ADP2114 Configurable Dual Output Synchronous Regulator by Analog Devices. Welcome to the training module on ADP2114 DC to DC converter. This training module consists of the ADP2114 overview, key features, application circuits, and a summary. Both switching controllers and switching regulators convert the DC input voltage to a fixed output voltage. In a switching controller, the output voltage is applied to an external MOSFET or bipolar junction transistor, but the MOSFETs are integrated into a switching regulator. No matter which method is used, the filter switch output voltage is fed back to a circuit that controls the power switch on and off, so that the output voltage remains constant regardless of input voltage or load current changes. Normally, the switching controller is used for load current greater than 5 amp applications, and the switching regulator is suitable for low or medium currents from 0.5 amps up to 5 amps. Points of load are voltage regulators or controllers that are located directly next to the load. Therefore, there's no further steps of power conversion required. The switch regulator features high conversion efficiency, flexibility, and configurability. With design tool support, it is easy to use. Its low noise characteristics make it suitable for high performance and sensitive applications. The switch regulator benefits point-of-load applications such as digital signal processor, ASICs, FPGAs, microprocessors, and microcontrollers used in communications, networking, industrial, healthcare, and a wide variety of other applications. Next, we will introduce the ADP2114, which satisfies a wide range of customers' point-of-load applications. The ADP2114 is a synchronous step-down switching regulator. It can be configured to deliver independent outputs at 2 amps and 2 amps, or it can be configured as a single output capable of delivering 4 amps. The device operates over an input voltage range of 2.75 volts up to 5.5 volts. Each output channel provides an adjustable output down to 0.6 volts and delivers up to 2 amps of load current. The integrated high-side P-channel power MOSFET and the low-side N-channel power MOSFET yield high efficiency at medium to heavy loads. Pulse skip mode is available for improved efficiency at light loads. The ADP2114 provides high efficiency and operates at switching frequencies of up to 2 MHz. The ADP2114 consists of 2 step-down DC to DC converters that deliver regulated output voltages V1 and V2. By modulating the duty cycle at which the internal high-side P-channel power MOSFET and the low-side N-channel power MOSFET are switched on and off, the output of the pulse width modulation comparator modulates the duty cycle by adjusting the trailing edge of the pulse width modulation that switches the power devices. Here's a typical application circuit of the ADP2114. From the diagram, we can see that the device is configured to deliver 2 outputs of 2 amps and 2 amps, and its output voltage is set to 1.8 volt and 3.3 volt. Changing the resistors RSFT2 and RSFT1 will change the output voltage correspondingly. The resistor FRFQ connected to FREQ pin and ground is used to set the switching frequency. In order to set the output current to 2 amps and 2 amps, a 4.7K ohm resistor has to be connected with OPC-FG pin and ground. 2 open drain power good outputs, power good 1 and power good 2, indicate the health of the converter output voltage. This schematic can be used to power DSPs and FPGAs. The ADP2114 can be designed into a broad range of applications due to its versatile nature. In Figure 1, the device is configured to provide two independent channel outputs, each at 2 amps with different voltages, 3.3 volts and 1.8 volt. In Figure 2, the ADP2114 is configured as a single output. We will introduce it in detail in the next page. In Figure 3, the device is configured as a 4-phase solution. In the interleaved configuration, the outputs of the two channels are connected together, and they generate a single DC output voltage. For this single combined dual-phase output, only Mode 2 in the OPC-FG options can be used. The two channels are 180 degrees phase shifted to reduce input ripple current and to reduce input capacitance. Effective output ripple frequency can be doubled, which halves the required output bypass capacitor value. Another advantage is the output inductor and capacitor can be smaller than a traditional single inductor output scheme. Reducing system noise. Normally the noise comes from two sources: noise coupled directly into the converter through supply ripple, and noise due to magnetic coupling effects. There are three mechanisms used to reduce system noise. The first is to synchronize the ADP2114 by an external clock or another ADP2114. This clock distribution approach synchronizes all DC to DC converters in the system and prevents beat harmonics that can lead to EMI issues. The slew rate of the switch node is controlled by the size of the driver device. Fast slewing of the switch node is desirable to minimize transition losses, but can lead to serious EMI issues due to parasitic inductance. Therefore, reduced slew rate minimizes EMI emissions without compromising conversion efficiency. The last is the output switching shifted 180 degrees between phases to reduce stress on the input capacitors and filters. The ADP2114 can achieve high power conversion efficiency up to 95% with a 5-volt input and a 3.3-volt output. The ADP2114 has a built-in pulse skip circuitry that turns on during light loads, switching only as necessary to maintain the output voltage within regulation. This allows the converter to maintain high efficiency during light load operations by reducing the switching loss. The high switching frequency of ADP2114 allows for minimal output voltage ripple, even with small inductors. The sizing of the inductor is a trade-off between efficiency and transient response. The ADP2114 also includes undervoltage lockout, with hysteresis, soft start, and a power good, as well as protection features such as output short circuit protection and thermal shutdown. These features are externally programmable with tiny resistors and capacitors. The ADP2114 soft start feature allows the output voltage to ramp up in controlled manner, eliminating output voltage overshoot during startup. The hiccup mode current limit feature provides output protection under short circuit conditions and periodically performs a re-entry or retry to start normal operation. The ADP2114 features open drain, power gut outputs that indicate when the converter output voltage is within regulation. Here's a schematic for powering the AD9268 ADC using ADP2114. One of its outputs supplies AVDD, the second output supplies DRVDD. The analog input of the ADC was supplied through a double ball-on input network, which converts the single-ended output from the signal generator to a differential input of the ADC. The sample clock source was a low jitter one-cell oscillator, which was also supplied through a ball-on circuit for single-ended to differential conversion. The ADP2114 can run asynchronously, or it can be synchronized to the converter sample clock without affecting the ADC's performance. Synchronization also allows for additional freedom in applications where it may be advantageous. The ADP2114 evaluation or demo board is a complete dual step-down DC-to-DC converter designed based on the ADP2114, a configurable dual 2-amp or single 4-amp synchronous step-down DC-to-DC regulator. The ADP2114 is a versatile step-down switching regulator that satisfies a wide range of user point of load requirements. The two pulse width modulation channels are 180 degrees phase shifted and provide plus or minus 1.5% accurate regulated output voltages. In summary, the ADP2114 is a highly versatile synchronous step-down switching regulator that can be configured to satisfy a wide range of customer point of load requirements. With the design tool support, it is easy to use. Designed for noise-sensitive point-of-load applications, the ADP2114 achieves high power conversion efficiency up to 95%, enabling designers to reduce time to market and provide higher reliability for medical, consumer, communication infrastructure, and industrial system applications.